we're going to add one more piece to the relationship that we've been working on. So far, when we're talking about refraction, we've got a relationship between the angles of incidence and the angle of refraction. We've got a relationship between the speeds. We've got a relationship between the wavelengths. And whatever ratio there is between the two is passed on to the other relationships as well. There's one more thing we're going to add, and that's the index of refraction. The index of refraction is just a ratio, as all the other things are. It's a ratio between the speed of light in a vacuum and the speed of light in whatever material we're talking about. So the speed of light in a vacuum travels the speed of light, 3 times 10 to the 8 meters per second. But through other materials, light doesn't travel the speed of light in a vacuum. It travels a little bit slower. So the speed of light through air is a hair slower than the speed of light in a vacuum through space. The speed of light through diamond is much slower than the speed of light through a vacuum or through air. And so we're going to look at how that index of refraction affects the speed of light, affects the wavelength, affects the angle. So the index of refraction is n. That's the index of refraction. It's equal to C over V. Okay, none of those letters are completely obvious as to what they are. Well, maybe the V for velocity or speed, but this N here is the index of refraction. C is the speed of light, and specifically C because it's a constant. The speed of light is always the same in a vacuum. Okay, and so it's C for constant speed of light, but we're just going to write speed of light. And then V is the speed of light in the material we're talking about. So we can calculate the speed of light in any material if we know what its index of refraction is. And so the speed of light in fluorite, we can figure that out if we know its index of refraction. And if you look at your formula sheet, here is a table of indices of refraction. So in a vacuum, the index of refraction is 1 exactly. That's because the speed of light in a vacuum is equal to the speed of light in a vacuum. And so when you take 3 times 10 to the 8 divided by 3 times 10 to the 8, you get 1 for the index of refraction. So that hopefully should make sense. And then the larger the number you get, the slower light is in that medium. Okay? And so if we're looking at fluorite, 1.433. I would encourage you to Google fluorite because you probably don't know what it looks like, but it's a really interesting mineral. 1.433 is the index of refraction. And so we can use that to figure out what the speed of light is in fluorite. So we know that the formula we're using is N equals C over V. N equals C over V. So the index of refraction we know is 1.433. The speed of light in a vacuum, you can look that up on your formula sheet as well. It's 3 times 10 to the power of 8 meters per second. And what we're trying to solve for is the V. And so it's a divided by V. I'm going to multiply by V to get it out of the denominator, and then I'm going to divide by N to get the V by itself. So V is equal to C over N. V is equal to 3 times 10 to the 8 meters per second divided by the index of refraction, which is 1.433. And so then I get a speed of 2.09 times 10 to the 8 meters per second. That's how fast light travels in fluorite, almost a third slower, or 33% slower than it does through a vacuum. So given that the index of refraction is just another ratio, we can actually add it on to Snell's law. And so it looks like this. Let's put together all of what we knew about Snell's law before. So sine of theta 1 divided by sine of theta 2 is equal to V1 over V2, which is equal to wavelength 1 over wavelength 2, which is equal to N2 over N1. Okay, so take note, this is angle 1, the incident angle, divided by the refracted angle, or the sine of those angles. Incident speed divided by refracted, incident wavelength divided by refracted. Refracted index divided by the incident index. It's flipped upside down, okay? And you'll notice that's because if we take our formula for velocity, v equals c over n, that was the rearranged version we just used in the previous example. This v1 is c over n1, and then v2 then would be c over n2, right? And so if we're looking at this part of the relationship over here, v1 is c over n1, v2 is c over n2. So let's just write that in here, c over n1 over c over n2. And when we get rid of all of this ugliness here, c over n1 divided by c over n2 is the same thing as multiplying by the reciprocal. So that's the same thing as going c over n1 times n2 over c. And then you can see that the c's cancel each other out, and we're left with n2 over n1. And so that's why that last part of Schnell's law is flipped upside down, it seems, because of the relationship of the index of refraction to the velocity. Okay, so you don't have to remember that that's why it's upside down like that. You just have to remember that it is upside down. So we can add this to Schnell's law. We can write this in another way, though, if we want to just talk about the index of refraction and the angles. We can write it like this: sine of theta 1 equals sine of theta 2, or divided by sine of theta 2 equals n2 over n1. But we're going to just rearrange it a little bit so it's not two fractions, so there's all a nice straight line equation. And so we're going to cross multiply. And so here's how it happens. n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. And it works out nicely that way because when you multiply sine of theta 2 by the top to get it out of the bottom, now it's attached to the n2, and you multiply the n1 to the top of sine theta 1, and so now it's attached to the sine of theta 1 part. So this is the relationship that you can use if you would like to connect the index of refraction to the angles of incidence and refraction. Let's do an example here. Light is traveling from a vacuum into ice. The angle of incidence is 46 degrees. What angle does it refract with? So let's say that, so this is the boundary between the two. We have to remember that. And I've drawn in the normal line as well. So light is traveling from a vacuum into ice. So top is vacuum, bottom is ice. I'm going to write that up here. Vacuum into ice. And so we have the angle of refraction is between the normal line and the wave ray. And so 46 degrees would be somewhere over there. So this is 46 degrees, or theta 1. And the angle of refraction, it doesn't tell us, right? But we can figure out what the angle of refraction is using Schnell's law. Or in this case, since we're trying to relate the angles to the indices of refraction, we can use n1 sine theta 1 is equal to n2 sine theta 2. We can use that. So we are always going to know n1 and n2. As long as we're told what the materials are, I suppose you're not always going to be told what the material is, but usually it's going to tell you it's going from a vacuum into ice, or it's going from air into diamond, or something like that. And you can always look up those indices of refraction on your formula sheet. Okay, and so we have to look up n1 and n2. The vacuum, n1, is 1.0. Okay, and ice, n2, is equal to 1.31. That just comes from your formula sheet. And so now we know n1 and n2. We also know the angle of incidence, theta 1, is 46 degrees. So what I'm trying to solve for is theta 2 over here. So I'm going to divide by n2 to get that sine of theta 2 by itself. So n1 sine theta 1 divided by n2 is equal to the sine of theta 2. And then I'll have to inverse sine that to figure out what the angle of refraction is. Okay, so now I know that n1 is just 1.0 times the sine of 46 degrees. That's the angle of incidence, divided by the index for ice, which is 1.31. And that gives me the sine of the angle of refraction. And when I do that calculation, I get 0.549. So all of this together is 0.549. That's the sine of theta 2. And then I need to do the inverse sine of 0.549, and that gives me theta 2 is equal to 33.3 degrees. Now, we should make sure that that actually makes sense. So we're going from a vacuum into ice. So the vacuum would be called the rare medium, and the ice would be the dense medium. And so light should slow down when it enters the ice. It should slow down, the angle should decrease, and the wavelength should decrease. And so we see that we started with an angle of incidence of 46 degrees, and we ended with an angle of refraction of 33.3 degrees. It decreased, which is what we should see in a denser medium. So let's take a look at whether this simulation follows what I just told you about the index of refraction. So we see that over here, the index of refraction for air is about 1.0. It's almost the same as a vacuum. If you look at your formula sheet, it's like 1.00029 or something like that. But to 2 decimal places, this is good enough. And then our second material here is water, and its index of refraction is 1.33. And so what we should expect is that if we use an angle of incidence of about 45 degrees, then it's going to bend toward the normal, because this is a denser medium than this one. The angle should get smaller. So if the angle between the normal and the wave ray is 45 degrees, then that angle over here should get smaller because we're going to a denser medium. Here we go. It's not a lot, but it does. So we can use this tool to measure the angles. So let's just make this 45 degrees, which it is. And then the angle of refraction between the normal and the wave ray is 32 or something like that, 33 degrees. So we see that it does actually follow that pattern, that the angle of incidence in the rare medium is larger than the angle of refraction. We also see this reflected ray over here, and it is leaving at 45 degrees, just like this one is coming in at 45 degrees. So it also follows the law of reflection.